Assalamualaikum and also a very good day I wish to Dr. Nur Hazila, as well as anyone else who may be watching. My name is Muhammad Shafiee Khaidzir, and in this video, I will be presenting my research project titled Neural Network-Based Inferential Control of Distillation Column in a Gas Processing Facility. Every equipment in a chemical plant, including distillation columns, will require a process control system to control its parameters within the desired set point value. While most variables could be controlled using conventional loops such as feedback control loops or cascade control loops, some variables lack an online measurement device, such as composition, and therefore it requires a special type of control loop. Therefore, this study implements inferential control strategy into controlling the overhead composition of propane from a depropanizer in a gas processing facility. The main objectives of this study are to model the dynamic relation of the depropanizer process, to model the estimator of the controller, and finally, to propose an inferential control strategy and evaluate the performance of the controller. In the methodology of this study, there are 5 main steps. Step 1 is data collection as well as determining variables relationship. Data collection was done to collect all the data necessary to perform the modeling for transfer functions as well as neural network estimators. Variables relationship must be determined through literature reviews because we need to see which variables of the distillation column are the most impactful and can be considered as the secondary measurement for the inferential control system. Step 2 is the development of transfer functions. Once the data has been collected and the variables relationship have been determined, we need to develop the transfer functions to correlate the process and the manipulated variable. The development of transfer functions was done by using the system identification toolbox using the transfer function type model in MATLAB. Step 3 is the development of the neural network. The type of neural network used is the feed-forward neural network, and the tool used is the neural fitting tool in MATLAB. The type of algorithm used in this sense is the Levenberg-Marquardt training algorithm. Out of all the sample data, 70% of the data is used for training, 15% of the data is used for validation, and the remaining 15% is used for testing. Step 4 is designing the inferential control system itself. The design of the inferential control system heavily relies on the fact that the neural network estimator is using 2 secondary measurements which are determined from step 1 of the methodology to predict the propane quality. The design of the inferential control system was done in Simulink MATLAB. And finally, step 5 is to evaluate the performance of the controller. This was done by running an open loop test for the propane quality to determine the initial parameters for the controller, the P, I, and D parameters, using the Ziegler-Nichols tuning rules. After that, a closed loop test is run using these parameters, and the parameters are fine-tuned using tuning rules to find the perfect P, I, and D values for the controller. And now the results are discussed. The first results that will be discussed here is the data collection as well as determining the variables relationship. From literature reviews, it was found that the overhead composition from a distillation column is most impacted by the top 3 temperature and the reflux flow. So these 2 variables will be used as the secondary measurements. From another research that was done on depropanizer dynamics, the data was collected. The data collected here is a total of 91 sets of data, as the sets of data here is when the distillation column, the depropanizer, is running at a steady state. So these are the sets of data that will be used for modeling in the next steps. Next is on the transfer functions. From table 1, it can be seen that the best model here is model number 1 with a number of poles of 2 and a number of zeros of 1 in the model itself. The R-squared value is 0.8831. So this model is the best model to be used for the propane quality. This can also further be proven in figure 1, where we can see that model number 1's graph is the one that most closely resembles the real data from the simulation data. From table 2, on the other hand, we can also see that model number 1 is also the best model to be used here. This has a number of poles of 2 and the number of zeros is 1, and the R-squared value of 0.8974. From figure 2, we can see that the graph for model number 1 is the one that most closely resembles the real data. So why are these models the best ones? Well, the answer is obvious. We can clearly see that the R-squared values for model 1 in both the propane quality as well as the top tray temperature is the best ones. However, if we take a closer look at table 2, we can see that model 1 and model 3 have the same value for R-squared. Why was model 1 selected? The answer is simple, because the number of poles and zeros in model 1 is lower than that in model 3. According to a study by Behrus, it was found that the lesser the number of poles and the number of zeros in a transfer function, the less complex the transfer function is, and the more controllable the transfer function is. This makes it so that it is much easier to predict the pattern of the transfer function, as well as to avoid any form of overfitting to this set of data. Next is the neural network estimator development. Previously, in the development of transfer functions, we manipulated the number of poles and the number of zeros. But in the development of a neural network, the number of hidden neurons is what's being manipulated here, which is from 6 to 14. Based on table 3, it can be seen that the best model here is model number 3. If you take a look at the regression values for training, validation, and testing, all of it is equivalent to 0.9999. That is close to unity. Taking a look at figure 3 here, which shows the regression plot for model number 3, it can be seen that it shows an almost completely accurate representation of the simulated data that is being used here. Now, it may be safe to assume that the higher the number of neurons, the more accurate a neural network is. However, when table 3 is paid close attention to, you can clearly see that models 4 and 5 have a bit of a lower value for the testing as well as the validation steps compared to model number 3. Why is this so? Well, it can be explained by the fact that the higher the number of hidden neurons, the higher the chances of the data to be overfitted, the model to be overfitting to the data it is using for training. This is why a lower accuracy can be seen in the testing step and the validation step for models with a higher number of hidden neurons. They have overfitted in the training data. With that, it has been concluded that the best neural network to be used for this inferential control system is neural network number 3 with 10 number of hidden neurons. Now, on to the main part of the whole study, which is the inferential control system design itself. Over on the left side can be seen here step input, which is where the set point value for the propane quality that is desired can be inputted here. The set point value is then deducted with the real value to produce the error signal, which is then fed to the PID controller. The PID controller will be producing the manipulated variable here, which is the reflux flow. This signal for the reflux flow is then fed to the overhead propane quality transfer function and the top tray temperature transfer function. And then the signal for the reflux flow along with the signal for the top tray temperature are both fed into the neural network estimator. These variables are the variables that are being used for the secondary measurements by the neural network estimator to predict the actual value of the propane quality. The actual value is, once again, as stated before, is deducted with the set point value to produce the error signal. This whole system closely resembles that of a feedback control system. The only difference here is that instead of a measuring device that gives the measurement at the bottom of the block diagram, we see a neural network estimator, an inferential estimator. The block diagram seen in figure 4 here is the complete inferential control system design for controlling the overhead propane quality of a depropanizer. However, what good is a control system if it can't actually control the variable that it is meant to control? This brings us to the final part of the results and discussion, the controller performance evaluation. Now, from the open loop test as well as the Ziegler-Nichols tuning rules, the initial tuning parameters were determined. These tuning parameters were then plugged into figure 4, the control system that was developed in Simulink, and then the closed loop test is run over and over to fine-tune and tune the parameters for the P, I, and D parameters for the controller itself. The final P, I, and D values are as shown in table 4, that is 215.4% for the proportional band, 62.04 seconds for the integral constant, and 6.254 seconds for the derivative constant. With these tuning parameters, and taking a look at figure 5 down below, can be seen that the propane quality can be controlled very well. The blue graph represents the step input, which was done every 200 seconds for the set point. And the red graph, the red curve, is the process response of the propane quality. It can be seen here that the red process curve, although it responds a bit slow, but it does reach the steady state value of in less than 100 seconds. This proves that this control system developed in figure 4, as well as the controller using these parameters and the transfer functions and the neural network estimator, are able to control the propane quality. However, it must be noted here that the control system, this control system, is only able to control from a set point value of 85% to about 90%, as seen in figure 5 here. This can be explained by the fact that the training data used for the modeling is for propane qualities from 85% to about 90%. The data is only used from the 85% to the 90% mark because this is the only point where the whole distillation column, the whole depropanizer, is operating at a steady state. With the available data, the dynamics of the process from 0% to about 80% is much too high for it to be able to properly model. To conclude, the aims and objectives of this study were all achieved. Similar to various other processes, the application of feed-forward neural network as an inferential estimator in inferential control systems is a valid proposal, as depicted in this study with the 0.9999 R-squared value for the neural network estimator. Using the transfer functions developed, the neural network estimator developed, as well as the inferential control system designed, it can be seen that the overhead propane quality can be controlled using these models and the system that was designed. Although the range is limited, the objective of this study, which is to control the overhead propane quality in the first place, is still achieved. And that concludes my whole presentation of the whole research. I would like to take this opportunity to thank my supervisor, Zalizawati binti Abdullah, for providing me supervision throughout the whole research for the past 2 semesters. And finally, I would also like to thank you, the watcher that paid attention throughout the whole video. Thank you very much, and Assalamualaikum warahmatullahi wabarakatuh.